All right, how's everybody doing today?
Good.
Okay, all right. Here for another class, so thank you for being here. So today we're going to start with a review of Watt's law. Remember we talked about Watt's law last time. We said that Watt's law is all about power. Really, it's just mostly a definition of power. We said Watt's law is really power equals voltage times current. That's basically all it is. It's a definition of electrical power. But there were several different ways that we could write that out, and several different ways we could use it depending on what we were trying to find. So we'll review that briefly, and then we'll go on to our main topic for today, which is midterm practice. So on Thursday, 2 days from today, we are going to have the midterm. So I want to practice a little bit about what's going to be on that test. Okay? So the midterm is really going to be all about finding the voltages and currents in a circuit with 4 resistors. And we've already seen that circuit. We looked at it a little bit earlier in the year. But I want to go over that again so that you're all familiar with that and ready to figure it out. So really there's 2 main ways that we can figure out these voltages and currents. We could figure it out with math, or we could figure it out by actually building the circuit and making the measurements. I strongly recommend that you do both. That way you can compare your answers from both methods, and hopefully if they come out the same, then that'll be an indication that that they are both looking good and that you probably got the right answers. If one is a little bit different than the other, then that might be an indication that something's not quite right and you want to go back and check. So we'll do both. We'll start with the circuit math to figure out the answers, and then we'll build the circuit and take measurements of the circuit voltages and currents and compare those with the answers we got with our math, and hopefully those 2 will match up. Okay? And then for the lab today, we're not going to cover any new material, but you will all get to practice this yourselves. Okay? So there is an online quiz that is just for practice for the midterm. So for the lab preview, or for the lab today, that's what I recommend you do. You look at that online version and do at least one, if not several, midterm practice sessions yourself. Okay? And I'll be here to answer any questions during that time. So that's our plan for today. Any questions before we get going? All right, cool. So then let's start with our review of Watt's law. So we talked about Watt's law last time, and we said that Watt's law is really this definition of power. So it says power equals voltage times current. And remember, power is the amount of energy that's being used at a particular instant. So this energy can be going towards things that we want, like lighting up a light bulb, or turning a motor, or sending radio waves out into the world. Those are all useful things that we might want to happen. So that's one thing that power can be used for. But power can also go towards wasteful things, like generating heat. So it's really important to understand both of these things, because we need to understand how much energy a light bulb might need in order to be bright, or how much energy a radio might need in order to broadcast our station out into the world, so that we can supply those amounts of energy. We also need to know how much energy is going into heat, so that we don't have a component overheat by accident and burn up or damage itself. Okay? So that's why it's important to understand about power. So we said that this is one way of writing Watt's law, but there are several other ways of writing it as well. So first of all, these things can be abbreviated. So power is P, and that's V times I. And this is a formula with 3 different components to it, kind of like Ohm's law. And also like Ohm's law, we can write it in a different way that allows us to figure out one of these things if we know the other 2. So we can write it like this: P, I, and V. Okay? So when we write it like this, we can use it just the same way we use Ohm's law. So if we want to find P, we just write down P equals, and we cover that up. We see it's I times V. Or if we wanted to find I, we would cover that up. We'd write down I equals, we'd cover that up. We see it's P over V. And if we wanted to figure out voltage, we would write down V equals, and cover that up, and see it's P over I. So if we can remember Watt's law in this form, that can be very useful. Also, sometimes we want to figure out power, but we don't know all of these things, but we might know something about resistance. So if we want to figure out power involving resistance, then we can use these other forms. We could say that power equals I squared times R, or power equals V squared divided by R. Okay? So these are all different forms of Watt's law. They're really just different ways of writing this same thing, that power is voltage times current. Okay? And there's a chart on page 53, I think, in your lab book, that circle that where the center of the circle are the things that you might want to find: power, voltage, current, and resistance. And then around the outside of that circle, there are the formulas for finding those things. Okay, so if you have a question that's asking you to find one of those things, you can refer to that chart and then just look for the formula that includes the things that you know. Okay? So let's do an example of Watt's law here. So let's say you're working in somebody's house and you want to install some lighting for them. And you know that that house has a 15 amp circuit breaker. In other words, it has a circuit, some power lines that run through the house that can handle up to 15 amps of current in them. If any current beyond 15 amps tries to flow through those wires, then this circuit breaker will trip and it will no longer allow current to flow. So you've got these wires that can handle up to 15 amps of current, and you've got you want to put a bunch of 100-watt light bulbs in this room. And you want to know how many of these light bulbs can you put into this room without tripping the circuit. Okay? And also, we know that this is a standard house. Okay? So standard house, standard building. So that means that the voltage of the electricity in the wall is 120 volts. Okay? So, yeah, the question is, how many bulbs can you put in that room without tripping the breaker? Okay? So this involves power. So this is going to involve Watt's law. So let's try and figure this out. So can anybody think of the first thing that we might do to try and solve this problem? Yeah.
15 times 100?
Not exactly, because the 100 is power. So we wouldn't just multiply current times power. Yeah.
Calculate the resistance.
We could do that. Yeah.
1 bulb.
Yeah. I might try and figure out how much current is in one bulb. So let's try and do that. Let's see how much current would be in one bulb. So for this, we would need Watt's law. So we know that power, we got power, current, and voltage. So here I would write down I equals, and then I would cover that up, and we see that it's P divided by V. So P divided by V. So for one bulb, the power would be 100 watts. And what is the voltage for each bulb?
120.
120, yeah. So the current for each bulb is 100 watts divided by 120 volts. So does somebody have a calculator? What does that turn out to be?
0.83.
Okay, so 0.83 amps. Okay, so each bulb takes 0.83 amps. So then, so 0.83 amps per bulb. And we know that we have 15 amps altogether. So if we say that we have 15 amps per circuit, or per room, say, and divide that by 0.83 amps per bulb, then what does that come out to be?
80.
Okay, so that is 18 bulbs per room. Okay, so that's how we could use Watt's law to figure out how many of these bulbs we could put on one circuit or in one room without tripping that circuit breaker. Okay? So, are there questions about that? Okay, so that was a quick review of Watt's law. So then let's go on and do our main topic for today, which is the midterm practice. Okay, so if you go on Canvas, you don't have to do this right now, but I just want to let you know, during the lab or at home, you can go on Canvas, and if you go to modules, there is a midterm module, and there's this midterm study guide. Okay, so if you click on the midterm study guide, that will bring you here. It'll have a review video. It'll have a video that shows you how to enter data into the midterm quiz. And then also at the bottom, there's a link to this practice midterm. So what I want to do here in class is I want to walk through this practice midterm and show you how you can actually do it yourself. And then after I'm done, you can go off and do it. Okay? So what it shows is it shows this circuit with 4 resistors. And up here at the top, it shows the resistor values. So here R1 is 1500 ohms, R2 is 1000, R3 is 330, and R4 is 1000 ohms. Okay? So what I'm going to do is I'm going to work through the math for this first, and then after I have figured this out using math, I'm going to actually build the circuit on a breadboard and make the measurements and see how closely they match up with my math. Okay? So that's the plan. So let's start with the math here. So let me just draw this out while I can see this here. So I've got a piece of paper, and I'm just going to draw this circuit. I know it might not be really easy to see this on the screen at the moment, but I'm going to draw it first just so that I get down all the values, and then I'll make it bigger on the screen so that it's easier to see. So I've drawn the basic shape of the circuit, and then I'm going to put down the values. So R1 is 1500 ohms. R2 is 1000 ohms. R3 is 330 ohms, and R4 is 1000. Okay, so there we go. All right, so this is the circuit, and then we have a 12-volt power supply over here. So now we want to figure out the voltages and the currents for all of our components. So I can make a little table over here, and we can say, let's see, V total, R total, and I total, and then V1, V2, V3, V4, and then also the currents. I1, I2, I3, and I4. Okay? So we want to figure out all of those things. So is there anything we can write down before we do any math? Yep, the total voltage. So that's just the voltage from the power supply. So V total is 12 volts. Okay? And then, so the next thing I would probably figure out is the total resistance. So the way that I would do that is I would look for any resistors that are in series or in parallel, and then I would write those down. So first of all, let's call this R1, R2, R3, and R4. Okay, so do you see any resistors that are in series or in parallel?
R3 and R4 in parallel?
Yeah, that's right. R3 and R4 are in parallel, we can tell because the beginnings of those resistors are connected to each other with nothing in between, and the ends are connected to each other with nothing in between. So R3 and R4 are in parallel. So we need to find their equivalent resistance. So can we just take one of those values and divide it by 2 since there are 2 resistors?
No.
No. We could do that shortcut if both resistor values were the same, but since they're different, we can't use that. So we have to use a different formula. We have to use that parallel resistance formula. So we say that R total equals 1 over, and actually we'll call this R34 because we're combining R3 and R4. So R34 equals 1 over R3 plus 1 over R4. Okay? So then I would say that's 1 over 330 ohms plus 1 over 1,000 ohms. Okay? And then I would get out my calculator. So let's see. Okay, so I would say 1 divided by 330, so that's 0.00303. So this equals 1.00303 plus, and then 1 over 1,000, I know that's 0.001. Okay, so then I just add these together. I say 0.00303 plus 0.001 equals 0.00403. So then I can say R34 equals, and then I just do that division. So I say 1 divided by 0.00403, and that comes out to be 248.1 here. Ohms. Okay? Now, we would want to do kind of a gut check at this point and see if this answer seems about right. So is there anything about this answer that makes it seem right or wrong when we're trying to find the parallel resistance between these two resistors? Well, so when we're looking at resistors in parallel, does the equivalent resistance go up or go down? Down, that's right. We're giving the electricity more paths to flow through, so the equivalent resistance has to be less. In fact, it has to be less than the smallest resistor in the circuit. So in this case, the smallest resistor in the circuit is 330 ohms, and we're saying that the equivalent resistance is 248. So is our equivalent resistance smaller than the smallest resistor here?
Yes.
Yeah. So that is a good indication that we're probably on the right track. Okay. So that's R34. So then we can use that and we can redraw this circuit with that equivalent resistance in place. So we can still have our 12-volt power supply over here. And then we still have this resistor on the top. R1 is still 1500 ohms. Now over here, well, yeah, on the bottom, we still have R2 is 1000 ohms. But now on the right, instead of having R3 and R4 separate, we just have a single equivalent resistance, which is R34, okay? And we know that that one is 248 ohms, 0.1, okay? So that's what we have there. So now we look at this circuit again and we try to see if there are any resistors in series or in parallel, and then we would combine them. So do you see any resistors that are in series or parallel?
All is in series.
That's right, all of them are in series. And we know that because the end of the first one is connected to the beginning of the second one with nothing in between, and the end of the second one is connected to the beginning of the third with nothing in between. So all of these resistors are in series. Okay? So then, how do we find the equivalent resistance of a series circuit?
Adding.
Yeah, we just add them together. So then we would say R total equals R1 plus R2 plus R34. And then we add those all up. So R1 is 1,500 ohms, and then R2 is 1,000 ohms, and then R34 is 248.1 ohm. All right, so if we add those together on the calculator, we say we would say 1,500 plus 1,000 plus 248.1, and that gives me 2,524.1. Okay, so then that would be my total resistance. So then I can redraw that circuit as just a 12-volt power supply. And a single resistor that is 2,524.1 ohms. Okay? So then that would be my total resistance up here. 2,524.1 ohms. Okay? So that's how we find our total resistance. So any questions about that? Okay. So then what would we look at next, maybe? Where could we go from here?
Can find I total.
Yeah, we can find the total current. And what law would we use to find that?
Ohm's law.
Ohm's law, that's right. All right. So let's remember Ohm's law. We can write it up here in the corner because we'll probably be using it quite a lot. We got V, I, and R. Now during the test, you will be allowed to bring in a sheet of notes, and you can write down whatever you want on that sheet of notes. So you don't have to memorize these things. You can actually bring that in with you and use that, okay? But in any case, this is Ohm's law, and we're going to use this to try to find the total current. So we write down I total equals, and then we go to Ohm's law, we cover up I, we see that I is V over R. So then that equals the total voltage, which is 12 volts, divided by the total resistance, which we said was 2,524 ohms. So we can do that on the calculator. We can say 12 divided by 2,524. And that gives me 0.00475. Five, 4 amps. Okay? So this is the current, and so we could convert that to milliamps if we wanted. We would multiply that by 1,000 to convert to milliamps. So if we do that, we say times 1,000, and that gives me 4.754 milliamps. Okay, so that would be our total current. You notice I'm not just calling it 5 milliamps. I'm not rounding that much. Okay, I'm keeping at least three, and probably 4 digits of precision or significant figures when I'm doing my math. Okay, so this is 4.754 milliamps. And then, so that would be the total current for the circuit. So that's the amount of current that's coming out of my power supply. So 4.754 milliamps. And how much is going back into the power supply?
The same thing that's come out.
That's right, the same thing. It's always the same amount of current going out and coming back in. So also 4.754 milliamps going back into the power supply. Okay? So now we know our total current. Can we write down anything else before we do more math?
Yeah,
Yeah, what can we do?
I1 and I2.
Yeah, that's right. We know that I1 has to be the same as the total current because the total current has to, there's no place else for it to go. The only place it can go is through this first resistor. So all of this total current has to go through that resistor. So then what is that total current? Or what is that current for R1?
4.75.
Yeah. So that's, yeah, 4.754 milliamps flowing through there. And the same thing down here. We know that we have to have 4.754 milliamps coming out of this resistor. So there has to be that much current flowing through it. So we have to have 4.754 milliamps flowing through that resistor as well. So I1 is 4.754 milliamps, and I2 is also 4.754 milliamps. Okay? Okay, perfect. So where can we go from here? Well, it would be nice to know the current through resistor 3, but I'm not quite sure that we can do that yet. Yeah, because we know that we have this much 4.754 milliamps coming out here, but then some of it splits off through I3 or through resistor 3, and some splits through resistor 4. So since they're not even, we can't quite tell yet. So I might look at a voltage. So what voltage could we look at?
V1.
Yeah, we could look at the voltage across resistor 1 here. And how could we figure that out? Ohm's law, perfect, because we know the current and we know the resistance there, so we can use that to figure out the voltage. So we'll do that. We'll come down here where we have a little room on our paper, and we say that V1 equals, we cover that up, we see that V equals I times R, so that equals I1 times R1, so that equals 4.754 milliamps times 1,500 ohms. So we can do that on our calculator. So what I can do is I can put in 4.754, and then this is milliamps, right? So I can't just multiply this times my resistor value. I have to convert this to milliamps first. So I could do that in a couple ways. I could divide it by 1,000, or I could use that EE function on my calculator. So I could say EE negative 3. So that's another way of saying 4.754 milli, okay? And then times 1,500 ohms, and that gives me 7.131 volts. So down here, that is 7.131 volts. So up here, I write 7.131 volts. Okay? And then I can do the same thing for R2 here. I know that current and I know that resistance, so I can figure out the voltage. And in fact, yeah. Okay, so let's just do that. So again, I put in the current, 4.754, and then E minus 3, and then times the resistance, 1,000, and that gives me 4.754 volts, okay? So across this resistor, we have 4.754 volts. Okay? So then the next part is a little bit trickier. We need to figure out the voltage across these resistors, R3 or R4. Okay? So there are kind of two ways that I would imagine we could do this. Okay? The first way is to use Kirchhoff's voltage law. So that says that if we look at all the voltages around any loop in a circuit, they have to add up to 0. So we could start here and we could go around this loop, and we know the power supply voltage and the voltages for R1 and R2, so the only one that would be missing is R3 over here. So we could figure out the voltage that way. The second way I would look at doing this is we could look at this circuit down here, and we could look at the current through this circuit. We know the current through each of these elements, and if we look at that current with this equivalent resistance, that could tell us the voltage across this part of the circuit. So let's do that. So, so here we could say V34 equals I34 times R34. So that's just using Ohm's law. And so that's I34, that's just the total current, so that's 4.754 milliamps. And then R34 is 248 ohms. So if we do that on the calculator, we say 4.754 E minus 3 times 248.1. That gives us 0.1145 or 0.1146. So, so then that would be the voltage across those two resistors. So, and since they're in parallel, we know that they are the same. So that is point. Oh, yeah, sorry, I screwed that up. So, yeah, that looked a little bit low. When I typed that into the calculator, I meant to say 248, but I typed in 24. I missed that. So let me do that again. So 4.75 E minus 3 times 248.1. Oh, I'm sorry. Let's try this one more time. 4.75 E minus 3 times 248.1. Okay. Thank you. So 1.178. So 1.178 volts, okay? So that is V3 and V4. And we know V1, we said, was 7.131. And V2 is 4.754. And so then the only thing left is I3 and I4. And we can figure that out using Ohm's law. So, so up here we can write I3 equals, we cover up I, we see it's V over R. So V3 divided by R3. So that we know that V3 is 1.178 volts. And then R3 is 330 ohms. So then we can do that on the calculator, and we get 1.178 divided by 330. And so that gives us 0.0036 3570. And that comes out in amps. So we can convert that to milliamps, and that's 3.57 milliamps. Okay? So that's R3, and then we can do the same thing for resistor 4. So we say I4 equals V4 over R4. So that comes out to be the voltage across, so that would be 1.178 volts again, divided by 1,000 ohms. So when you have a voltage divided by 1,000 ohms, then the current just comes out to be the voltage in milliamps. So that would be 1.178 milliamps. Okay? So then we can write down those values. So I3 is 3.57 milliamps, and I4 is 1.178 milliamps. Okay, so that's everything we needed to figure out about this circuit. So I know that was a lot of math, and that was probably pretty tedious listening to me just kind of sit up here and rattle off formulas. But that's how we can get that. Yeah?
There's one part I was confused on.
Uh-huh.
So when you went from 0.00403 to 248 ohms,
Uh-huh.
how did you get to 248?
So this is 1 divided by 0.00403. So this is a 1 up there divided by that. So if I just do that on the calculator, so I type in 1 divided by 0.00403, that gives me 248. Yeah. 0.1. Okay, so I know that was tedious, but the thing is that's the way we go through it. And when you go through a lot of math like that, there's a good chance that you're going to make some mistakes. I know I made at least one along the way. I had to backtrack. So it's good to kind of check things and do some sort of confidence checking along the way to make sure that things are looking like they're on the right path. Okay, so so there's a couple things that we can check here to kind of help ourselves see if we're on the right path. Bless you. Like the first thing was that the parallel resistance should be smaller than the smallest resistor of those two. So that was fine. The smallest resistor was 330 ohms, and our calculated resistance was 248. So that was less than either one of those. So that was good. The next thing we could look at is that we know that these two resistors are in parallel. So what does that mean about their voltages? So in a parallel circuit, are the voltages the same or different?
Different.
The same, yeah. So they have to be the same. So if we look at V3 and V4, they should be the same, and they are here, so that's good. And then we know that the current, well, all the current for this circuit has to flow through R1 and also through R2. So those currents for R1 and R2 should be the same. So I1 and I2 should be the same. So they are here, so that's good. And then the last thing is we can look at the voltages around a loop, and they have to add up to 0. Another way of saying that is that V1 plus V3 plus V2 have to add up to 12 volts over here. So we can do that as a check. So we can say V1 is 7.131 volts, and then V2 is 4.754, and then V3 is 1.178. So if we add those all together, okay, so did I type something in wrong? Let's see, because that came out too big. So 7.131 plus 4.754 plus 1.178, giving me 13. 11.8. So, okay. So that tells me that I did something wrong. So then I would have to go back and check that out and figure out where the problem was. Okay, so well, so then rather than go through and sort of just do this math all over again, what I'm going to do is I'm going to start to build this circuit on the breadboard and see how how my breadboard circuit compares with this circuit, and then see if that can help me figure out where I went wrong. Okay. So yeah. So let's see what's going on. All right. So let's build this circuit on a breadboard. So I got a breadboard here, and what I'm going to do is I'm going to try and make this breadboard look a little bit like, well, as much like the drawing as I can. Okay. So actually, before I build the circuit, I'm going to look at my resistors, and I'm going to actually measure their values and make sure that they are correct, so that I know that I am using the right resistors, and I didn't grab one out of a bin and it was the wrong one. Okay, so so the first thing I'm going to do is I'm going to look for a 1500 ohm resistor. So we can use our color codes to help us figure out which resistor this actually is. So, so what colors would we have for a 1500 ohm resistor? So the first number that we would have there is a 1. So what is the color for 1?
Black.
Black is the color for 0.
Brown.
Brown, yeah. So we would need to find a resistor that starts with a brown mark, and then the next number would be 5. So what color is 5? Yep, green. And then we have 2 zeros. So what is the color for 2?
Red.
Red, yeah. So we're looking for something that's brown, green, and red. Okay? So those are the colors that we're looking for. So here are our resistors. So these colors are not very vibrant, and they can be really, really hard to see sometimes. So I think that this top one is brown, green, and red, even though that, so we'll flip this around so that the gold band is on the right side. So that's brown. I think that this middle band is supposed to be green, even though it's really hard to see. Looks more like black from this angle. But I think that that's brown, green, and red. But I'm not sure. So maybe, actually, that might be a black one. That might be the 1000, and then this one at the bottom might be the brown, green, and red. So it's really hard to tell And it's possible I even grabbed 2 of the 1,000 ohms. Well, you know what? I think, actually, yeah, I think that those are both 1,000 ohms. It looks like I tried to grab a brown, green, and red one, and I didn't get one. So let me grab another one of those.
You sure?
I don't know for sure, but let me grab another one here. What I can do to check it is I can use the meter to, yeah, that looks better. I can use the meter to actually, we can hook it up to the meter and then see for sure, okay? So, yeah, so that one looks better. All right, so that one at the top now is the brown, green, and red. The other thing you can do that can be helpful sometimes is you can shine a light on the resistor, or if you have a cell phone, you can use that and take a close-up picture of the resistor, and that can help you to see what's going on. But if you're not sure, the final say is always the meter. Okay? So I'm going to use this multimeter and check that resistor value. So I'm going to put the meter into resistor measuring mode. I'm going to put that there. And then I'm going to, I put the black lead in common as always. I put the red lead over in the right-hand port to measure voltage and resistance. And then I'm going to grab this resistor in the 2 leads of my meter. So I connect that, and I see that that's 1,482 ohms. So that is looking pretty good. So that's pretty close to 1,500 ohms. Okay, so that's fine. So now I'm going to put this resistor into my board in this position near the top of the board on the left-hand side. Okay, so that's where the 1,500 ohm resistor is in my diagram. That's where I'm going to put it on the board so I don't get confused. And then I'll go on to R2. So R2 down here is 1,000 ohms. So what is the first color for that resistor? Yep, so 1 is brown, and then 0 is what? Black. And then we've got 2 more zeros, so what's the color for 2?
Red.
Red. So yeah, so that should be a brown, black, red resistor. So if I come here, that would be this one, hopefully. So I look at the colors to get the one that I think it is, and then I will check it in the meter. I always check it before I put it in my circuit. So I'm going to check that, and yeah, that's saying 0.985 kilo ohms or 958 ohms. So that's going to be a 1,000 ohm resistor. So I'll put that one down here on the bottom left side of my circuit, just like it is in the diagram. All right. And then R3 is 330 ohms. So what color is 3?
Orange.
Yep, so orange, and then another orange, and then 1 0. So what color would that be?
Brown.
Brown. Yeah, so we're looking for an orange-brown resistor. So that should be,
The middle.
Yeah, this one in the middle. Remember, the yellow band is always at the end. Or, I'm sorry, the gold band is always at the end. So, yeah, so this would be orange, orange, brown. And that one is brown, orange, orange. I don't... so we don't, yeah, we don't need that one. So that one must have been put in the wrong bin. So I grabbed that one out of a bin, and it was just the wrong one. Anyway, so we've got orange, orange, brown for 330 ohms. So we think that that's 330, but we're going to double check just to be sure. So we're going to grab that in the meter leads. Hey, right on the money. All right, cool. So that's our 330. So for this one, I'm going to put it in the board so that one end of the resistor is in the same row as the top resistor, and then the other end is in the same row as this bottom one, okay? So, so I've got that. And then the final resistor here should be my last resistor in my circuit, which is a 1,000 ohm resistor. So let's check that. So I'll grab these two leads with my meter, and it comes out to be 985 ohms, okay? So pretty close to 1,000. So I'm going to put that over here on the right-hand side of my board. Just like it's on the right-hand side in the diagram. Now, in this diagram, there is a connection from the top of R3 to the top of R4, and from the bottom of R3 to the bottom of R4. So I need to make those connections in my circuit as well. Okay? So I'm going to go from there over to there with a jumper wire, and then I'm going to make the bottom connection with another jumper wire. So from there over to there. All right. So now my circuit should be pretty much set up. The last thing I'm going to do is I'm going to connect a wire from there down to there. Or I'm going to connect one jumper wire at the top where I'll connect the positive side of my power supply, and then the other wire at the bottom where I will connect the negative side of my power supply. All right? So now I can do the first thing that will kind of help me check between my circuit and the circuit that I built on the board and the calculations that I did. Okay? So what I'm going to do is I'm going to measure the total resistance of my circuit. And the way I do that is I measure from one side of the circuit to the other. Okay? When I do that, so I'm getting an overload there, so I'm going to go up into the next setting. So this is saying that the total resistance is 2.7 kilo ohms. So that's a little bit higher than I calculated. I calculated 2.5 kilo ohms. So let's see. Is that where I screwed up? Let's see. What's that?
The DMA is not clear.
Oh, sorry. Yeah, thank you. So this is saying that we have a total resistance of 2.71 kilo ohms, but in my calculations I got 2.5 kilo ohms. So let's just go back and check on this. So
Maybe the way you jumped it?
well, I think that my circuit is set up pretty well. Let me check this parallel resistance for these two resistors. So yeah, so the parallel resistance came out about right. So 247, I said it was 248 ohms. So that seems about right. So then, so this should be 1,500. So that should be 1,700, 2,700. Yeah, so yeah. So yeah, so that's where I screwed up. I screwed up my total resistance. Somehow I added these together and yeah. Yeah, it should, so yeah, so I screwed that up right at the beginning there. So this calculation right there, so I have 1,500 ohms plus 1,000 ohms plus 248.1 gives me 2,748. And somehow I wrote that down as 2,524. So
You added
24.1 instead of 248.1. So yeah, so there you go. So that was the problem. So I screwed up this first total resistance, and then that threw off all my other calculations, okay? So that was my problem. So if I was doing this on the test, I would probably go back and redo my math starting from there. But what I'm going to do here is I'm just going to make the measurements on the actual board, and then I'll show you how to do that and how to enter the data, and hopefully that will give us the right answer. Okay. All right. So anyway. So I guess the lesson to take away from this is that it's easy to make mistakes doing math or doing the board. So that's why it's important to figure out the answers both ways so that you can compare them to each other. Okay. All right. So we've got this circuit set up. So now we're going to connect this circuit to our power supply. So we're going to turn on our power supply. Let me All right, so here's our power supply. So we're going to turn the current all the way up. We're going to use the voltage supply here and set that to 12 volts, as close as we can. It's really fiddly, so, just do your best. Whatever, close enough. All right, and then we're going to plug the black lead into the black port, and then the red lead into the red port here. And then we're going to connect these leads to our breadboard. So we're going to connect the black lead down here and the red lead up here. And now we are going to have we're going to make the measurements for this circuit. So we're going to measure the voltages and the currents for each resistor. Okay? So first of all, I'm going to measure the voltages. So I'm going to put the meter into voltage measuring mode. So I'm going to leave the red lead in the right-hand port, and I'm going to turn the dial over into the voltage region. All right, and then in order to measure voltage, I'm just going to attach the meter to the two ends of each resistor. Now, I could clip directly onto those two ends of the resistor, but I don't like to do that because that has a tendency to pull the resistor out of the board. So what I do instead is I just grab onto two jumper wires, and then I plug them into the same rows as the ends of those resistors. So for this first resistor, I'm going to plug the leads in there. So that gives me 6.57 volts. So then what I would do is I would come over here to my diagram, and I would say that the voltage for resistor 1 is 6.57 volts. Okay, and then I can do the same thing for the other resistors. So I can measure the voltage across this bottom resistor. So again, I plug these jumper wires into the same rows as these resistors. And so then I see that the voltage across R2 down there is 4.37. So I would put that in, 4.37 volts. And then I can measure the voltage across resistor 3. I can go there. So then I get 1.1 volts. And then I can measure the resistor, or the voltage across resistor 4. Same thing, I plug in the jumper wires on the two sides, and I see that that's 1.1 volts. And then I measured the total resistance earlier. We said that that was 1.7. Yeah, thank you. 2.748 kiloohms. Now, if I try to type in K here, this gives me a warning. It says this is not a decimal or integer value. Okay, it doesn't like the K. You can't just type in K for kiloohms here. You actually have to convert this into ohms. So to go from 2.74 kiloohms to ohms, you would multiply by 1,000. So that would give you 2,748 ohms. Okay. And then we're on to our current values. So measuring current is a little bit more tricky. Remember, there's a couple things we have to do. So we have to put the meter in current measuring mode. So that means we have to move this red lead over to this port that says MA for milliamps. Remember, the black lead stays in the common port there. And then in order to measure current, we have to partially deconstruct our circuit. So the way that I do this is when I want to measure the current through a resistor, what I can do is I pull out one end of that resistor, I plug in a lead where that resistor used to be connected, and then I've got two loose ends of the circuit, the end of the resistor and the end of this wire. And then I connect those two loose ends to my meter. And then I put the dial for my meter into the current measuring section. And then this gives me the current reading. So, so this current says 4.42, and the unit for that is milliamps. So, so this is the current through resistor 1. Because that's resistor 1 on the top, so that's 4.42 milliamps. And then I pull this apart, and I put the circuit back to the way that it was originally before I go on.
So you just took out the resistor, put the thing in it, and then measured it?
So so let's do it again. So I took out one lead of this resistor. We're doing this for the bottom resistor now, R2. So I took out one leg of that resistor. Then I plugged in a wire where that leg used to be connected. And then I hooked my meter to these two things that are sticking up. So to that wire and the leg of that resistor. And then that gives me 4.42 milliamps again. Okay? So, and then when I'm done, I just reverse that process. I pull out the wire, I disconnect my meter, and I put that leg of the resistor back into the circuit so that everything is back the way we started. And I do that before I go on so I don't get confused and I don't leave anything hanging out where it's not supposed to be. So then I'll just do that for the last two resistors. So that resistor there, I pull the resistor out, I plug a lead in where the resistor used to be connected, and then I connect to the two ends that are hanging out there, the wire and the resistor. And then that gives me 3.3 milliamps flowing through there. And then I'll put everything back. And then I'll do that for the last resistor. I'll disconnect that leg. I'll plug in my wire. And then I will make my connections. And I get 1.1. Okay. All right, so that's looking good. And then the last thing that I want to do is I want to measure my total current. So this is the current that's coming from the power supply or going back to the power supply. So in order to do that, I have to break my circuit apart where the power supply attaches to my circuit. So that would be up here at the top of my board. So I can pull this power supply lead out of the board and then plug in a jumper wire where that power supply used to be connected. And then I can attach those two ends to my meter. So I'll attach my meter to this power supply lead there, and then, or that jumper wire, and then the power supply lead. All right, and then we get 4.42 milliamps there. Oops. Okay, so so that is, those are the numbers. That's how I can measure my circuit. Now, again, we should do some kind of gut checks here to see if this looks about right. So we hope that the voltage across R3 and R4 should be about the same because they're in parallel, and that is the case. They're both about 1.1 volts. We hope that the current through R3 and the current through R4 together add up to the total current, because the total current should be flowing in. So we have 3.3 and 1.1, that adds up to about 4.4, and the total current is 4.42, so that looks about right. And then the current through R1 should be the same as the current through R2, should be the same as the total current, because they're all connected to this power supply. And yeah, we have 4.42 from the power supply and 4.42 for R1 or I1 and I2. So those are all looking good. Like I said, if I was doing this test and I had screwed up my math and it didn't quite match my measurements, then I go back and do my math to double check, but I'm not going to make you sit through all of that again. You've seen the process, and we figured out that I just screwed up the total resistance at the beginning, and then that threw off all my other calculations. So yeah, so in this case, I'm just going to submit this and then see how we did. So I'll hit the submit button, say OK, and hey, we got 100%. So that's awesome. But, you know, sometimes you don't get 100%, and that's OK. And if you don't get 100%, it's good to go back and figure out what happened. So if you're curious about what happened, you can click on this tab that says Review Questions, and you come back here. And down here at the bottom, there's this key button. So you should click on the key, and then that shows you all of the values that the computer calculated. So this shows you the answers that the computer thinks are right, and then you can compare those to the answers that you actually got. Okay? And you'll notice that the answers that the computer calculates are not exactly the same as the ones that we got, and yet we still got the right answer. Okay? That's because the computer allows for a tolerance. So I believe that there's a 10% tolerance allowed between what it thinks is the right answer and what it will accept as a viable answer. Okay? Because as we all know, things aren't perfect in the real world. So your resistor values are not going to be exactly the same as the specified values. Your voltage on your power supply isn't going to be exactly the same. So there's going to be some slight variation, but the more precise you can be, the closer you'll get, hopefully, to the calculated answer, and the better chance you'll have of getting the correct values. Okay? If you round too much, that can throw you off. If you make inaccurate measurements, that can throw you off also. So try to be as precise as possible. So yeah, so that's how you can do the midterm. So I showed you how to do the math, I showed you how to build the circuit, and I showed you how to make the voltage and current measurements on that circuit. So are there any questions about that? All right, then I will take attendance and I will let you go. And I think, yeah, I would strongly suggest that you do the practice here during the lab time.